In this video, we're just going to kind of riff on circles, and I'm just going to do one big long video. I'm not going to do any questions. I'm just going to do the theorem, the theories, the basic axioms that you need to have, the bare minimum in NCEA circle geometry. Okay, so I've gone on AI actually, and Grok has given me this HTML, which works fantastic. Everything works brilliant. It just has no personality. And I went on ChatGPT, and it gave me this kind of thing with lots and lots of whistles and bells, and really, really colourful. Half of it doesn't work, but it looks cool. So I'm going to be flipping between both of these. But the main theorem is on here, and I'm going to put both of them on the website. So let's look at parts of the circle first that you need to know. We have a circle. It shouldn't really be a big shock. You should know what a circle looks like. It's a loci of points equidistant from a central point. If you want the formal definition of a circle, if the center is around about here, then the perimeter, aka the circumference, is this dark orange bit here. There's a bit of debate. This technically, I think this is actually the perimeter of a circle, and the circumference is the distance around the circle, I think, from memory. But if you call it circumference, perimeter, same thing. Probably stick to circumference. Okay. The diameter is the distance from one side of the circle here to the other side of the circle there, which goes through the center. So it's the longest possible line that you can draw, straight line, through a circle. Note the difference between the diameter and the radius. I'm just going to move that up. So here we have the radius. The radius is the distance from the perimeter, the circumference of the circle, to the center of the circle. And it's denoted by the letter R. And this is the measurement that you will come across quite a lot in circle geometry when you have pi r squared, 2 pi r. They're not really looking for the diameter. The radius is really, really important. Okay. Let's have a look at a chord. And I'm just going to move this one around. So here we have a chord. Now, a chord is just a straight line between 2 points on the circle. There is one little caveat there. It has to be less than the circumference. And it could be argued that the diameter and the chord, the diameter is kind of a special case of the chord. If we have the diameter there and we kind of move this around, we could have the chord and the diameter on top of each other. But for now, we're just going to say that the chord is a straight line between 2 points that is less than the diameter. Fair enough. Now let's look at I want to look at a segment. Take the diameter away. So a segment is this pink area here, which is kind of defined by this chord. So it's the pink area. So it's got to be less than half of the circle because it would be the diameter. And it's the area there, and it has its own formula that we would use to work it out. We're not really worried about it just at the moment, but this is a segment. Okay, this is a sector. So I'm just going to take that off. So notice the difference between a sector and a segment. A sector and a segment. Not the same thing. Kind of the same thing though. Notice that the sector is this entire wedge here. Almost like, it kind of looks like Pac-Man. Almost like a pizza slice. But notice that the segment is kind of a subset of the sector. So here's the segment, here's the sector, is the whole slice. So I guess the segment is the crust, and the sector is the whole slice. And again, there are formula that we use to work that out, but we're not going to worry about it for now. All right. Take that off, take the chord off, and let's look at a tangent. Tangent is a straight line that just touches the circle and goes on. Straight line touches it once and it's tangent. This is important later on in calculus. We can move it around like that. This is an important concept later on when we come to use vectors and in physics and in calculus especially. But just for now, just so you know what a tangent is. So again, it's a straight line. It touches the circle once and only once, and then goes off in its merry way. All right, first proper theorem. The theorem is the angle at the center. This is this angle here is always twice the angle at the circumference on the same arc. So the arc is this piece of the circle around here. Right, so this angle is on the center. It goes from A to B. This angle is on the perimeter, on the circumference, that goes from A to B. This angle here is always going to be twice this angle here. So let's have a look at this one. So we can move this around. So this is the angle on the center, 120, half that is 60. And notice what happens when we move B around. It just stays exactly the same. So when we move this, oh, I'm going to move the other one, that around, this one moves out this way, but this one sort of contracts by the same amount. So this is always 60 degrees. When this is 120 degrees, so if I move it around, it's still 160, and even if I go like that, it's still going to be subtended on the same arc. And if I move A around, $150, $75. Okay. So what I'm going to do, I'm going to take the I'm going to leave that there. A, B, helper. Yes, I'll leave that there. So I want to move this, move the A, so that it's at 180 degrees. So it goes all the way across through the center to the other side. So this triangle here, I'm going to tell you something groundbreaking. It's not a triangle. Think of it as a quad where this angle here is 180 degrees. So this is 180 degrees. This is going to be 90 degrees. Yep. Quad. 165. 150, 75. Okay, half and half. We move it around. 180 degrees. We have instantly a right angle triangle. And we can move B around, and it's always going to be a right angle triangle. So this is kind of a heads up of a rule that's coming later on. The angle, if it cuts a semicircle, is always a right angle. It's always 90 degrees. All right, next rule. So this is the theorem that two angles on the same arc are equal. And this is kind of a butterfly question. If you look, this kind of looks like a butterfly. There's one wing, there's the other wing. What this says is that we have an angle here which is subtended to this arc here between A and B. So one leg goes to A, the other leg goes to B. We have another angle here. One leg goes to A, the other one goes to B. What this theorem says is that this angle here is always going to be the same as this angle here. And because this angle here is opposite this angle here, so they're the same, this angle here must also be the same as this angle here. I'm going to move this up a little bit. So it doesn't really matter where I move D, because the legs kind of are planted on A and B, this angle is always going to be the same. So as this kind of leg moves this way, this leg is going to move this way to sort of compensate for that. And it's going to stay at 45 degrees. It's going to be set. So if this is 45 degrees, this must be 45 degrees. This angle here, I don't know what it is, it looks like about 30 degrees. This angle here must be 30 degrees. As long as these are straight lines and they're on the circumference, on the perimeter, they're going to be the same angle. There is a kind of a rule that comes from that, which is sort of shown best here. If this arc length is the same, so if this line here is the same length as this line here, these angles must be the same. All right. So if we move this around any, it's going to throw out our measurements. So these have to be straight lines, and these are not straight lines. This is kind of kinked. Reset it. So the theorem is, if this length is the same as this length, the angles must be the same. So these must be similar triangles. That is, that the angles are the same and the ratios are the same. Fair enough. The next rule kind of does your head in a way, and it pertains to quadrilaterals. So quadrilateral just means a four-sided polygon, so all of these sides are straight. If the four sides are inscribed, that means touching the perimeter but not going over it, then something really curious happens. We know that any quadrilateral, all of the angles add up to 360 degrees. We've covered that. What this theorem says is that the opposite angles, this angle here and this angle here, add to 180 degrees. So therefore this angle here and this angle here also add to 180 degrees. And it's shown best using this one. So we have C, so let's move C to there, and I move A. It doesn't matter where I put A, as long as it doesn't overtake it, it's always going to add to be 180 degrees. It's just really, really strange. So if I move D to there, so if I keep D and B steady and I move A around, it's always going to add to 180. 105 plus 75 is 180. And if I move C around, it's always going to be 105 degrees, as long as it's between D and B. It's just a really, really curious property of circles. So again, this is the quadrilateral rule. Opposite sides are supplementary. Supplementary just means they add to 180 degrees. This next one we've kind of covered. So this is a theorem that if a triangle is inscribed inside the circle and it goes through the center of the circle, it must be a right angle triangle. Okay, just sort of trust me on this one. So we can deduce that this line here must go through the center. So if we draw this line and then we move these around a little bit, so let's move that around here, and we get another one. We have this straight line now. We can deduce that both where those lines bisect must be the center of the circle. So again, if this line, I was going to say tangent, I guess you could say the hypotenuse in a right angle goes through the center of the circle, the triangle that's formed is always going to be a right angle triangle. So it's a really, really important rule to know. Quite often you'll get question in exams and in tests, and it'll be kind of they'll give you this one, and then they'll say AC goes through the center. What is this angle? And you can just automatically say 90 degrees. Notice 90 degrees and 90 degrees, they add to 180 degrees. So therefore this angle here and this angle here added together must also equal 180 degrees. This rule is kind of self-evident, but it's the rule of perpendicular tangent point of contact. It sounds wordy. What it means is that if we draw a line from the center, which is O there, to the tangent point, and then we draw that tangent point, so remember that line that just touches the circle and nothing else, and then moves off, this angle is always going to be 90 degrees. If we move this around, always 90 degrees. That is kind of self-evident, but it gets to be really, really important later on. And we can move this around a bit. It's really, really, really important in physics that we know this fact. When we have circle physics, so something is if this thing was rolling down this hill, we would need to know that this is at right angles, and we would need to know where the center was. So this looks really, really simple, but it is actually really, really important to know this one. Alright, nearly there. Last rule that we need to know for the bare minimum for NCEA circle geometry, and that is that this triangle here that we create, so 3 points here, one of them is the tangent, the opposite angle, this one here, must be the same as this angle here. Alright, so I'm just going to take these off. This angle here is the same as this angle here. Okay. why? They just are. I'm not going to do a formal proof. There is a formal proof, but it's about 60 pages long, believe it or not. I might leave the link. Just know the rule for now. The angle which is opposite the tangent equals this angle that's made, this kind of angle of incline between the other leg of the triangle and the tangent line. Okay, that's the bare minimum you need for NCEA geometry, circle geometry. I'm going to do questions later using these theorems, but every question that you do will be related back to this theorem, and quite often they will ask, what is this angle? And then they'll say, what rule lets you know that this is true? So knowing these theorems, having a good intuition about how they work and why they work is quite important. Don't go into, obviously, formal proofs, but just kind of know these rules, because some of them are not intuitive, but it'll help you a lot in your tests.